All right, let us start. So, good evening, everyone. I am Saptarshi Dev. I am a PhD scholar at the Electrical Engineering Department of IIT Bombay. These classes are the doubt clearing classes of the NPTEL course Electrical Machine 1, and this is the week 8 doubt clearing class. This is a 12-week course, and the topic of this week is DC machine. Mostly its types and some basic operation of it. Okay. So yeah, this session happens every Saturdays, this time 7 to 8 p.m. for an hour only. Before we start, can I get a response from you to know how many of you have watched some or all of the videos of this week? Can you raise your hand using the raise hand feature of Google Meet? Some or all of the videos? Pushpraj has watched some. Only Pushpraj's hand I can see in every session.
No, sir.
Okay, then we will start with DC machine types depending on their field connection. Okay. So last week I told that I will discuss why DC machines are still used. I did not do that. So maybe today we will see why it is still used or still taught also. So depending on types, so last time I discussed that to generate torque from any electric machine, you need two things. And basically, there are interaction between two fields. One is the armature field, and other one, say armature flux, and other one is the flux created by the field winding. And the torque is proportional to this phi A times phi F times sine delta. So this is torque. So you can understand that two entities are required, at least two entities are required so as to get torque from an electric machine. So two entities, one come from stator, other come from rotor, like that. Now, the thing is how to get this phi F. In case of DC machine, we get it from the field winding. Field winding, we get this. Now, the field winding can be connected in several ways. So depending on the DC machine can be divided into several branches. So we will see the DC machine, depending on this kind of classification, can be classified into two. One is self-excited. I should have written it later. Another one is separately excited. Excitation means field. Excitation means field. Irrespective of any machine, when you say excitation, that means field. So self-excited and separately excited. So the concept of DC machine is actually very easy. You create field from one and you have armature on the other. Armature rotates inside the field and you get the torque or electrical energy depending on the operation, whether it is motoring or generating. You can stop me anytime if you have any doubt and ask me any question if you want. Okay, so first we will see what is separately excited. So as we said that there are two things. One is the field winding. Other is the armature. Right? Now the armature is there invariably like this. Anyway, looks very bad. So this is the armature, let us say. And these are the brushes. What is brush? What is commutator? Why at all brushes are required? These things we discussed in the last session. So this is the armature, right? And the armature is always connected to the principal DC bus. It can be any kind of DC machine. It is always connected to the DC bus. May it be generator, may it be motor, it is connected to the DC bus. For generator, it can be DC bus, it can be a load, whatever. But this is the armature winding A. I will write A. Okay. Now there is a field. There is a field. It is customary to draw DC machine field in perpendicular with armature in this fashion. We will see why if we have time. So this is the field winding. So if you have done experiments on DC machine in your university laboratory, or maybe have seen it somewhere in industry or whatever, you will see that most of the machines that look like this, there is an outer cover and there is a box mounted on it where all the connections are there. If you open the cover of the box, you will see all the connections. This box is called terminal box. Terminal box. Now, if you look into the terminal box, you will see there are several windings. Not windings, several terminals. So like this. Now, conventionally, these terminals are named like this in case of DC machine. A and AA. So A and AA, these two means these two are the terminals of the armature winding. And F and FF are the terminals of the field winding. This name is very common, this is used. So now first we will see what is separately excited DC machine. So we have a armature here, we have field here. Now separate excitation is, I will keep a copy of this, we will need this. Separate excitation means this field winding, this is the field winding. I will write say F and FF here and AA here. So this field winding is supplied from some separate source. Some separate source. This may be this source itself, which is most of the cases true. We do not get another source for field, but this can be something else also. That is, you have a control on it when you have a separately excited machine. Another DC bus. I will write say DC bus 1 and DC bus 2. So this is separately excited. You can control this current of this field winding and you can do many things on it. So it has obviously this whole, do not think that this field winding is somewhere else than the armature. They are on the same structure, but the connections are made like this. So this field winding is supplied from a separate DC supply. Most of the cases, these two supplies are the same. They are kept like they are parallel. Okay, so that is one kind of separately excited DC machine, only one. We will now come to self-excited. Now self-excited, there are several ways of connection. One of the connection is like this. One of the connection is connect paste. Yeah. Say we had this DC machine, armature. The first one that we will discuss is A, shunt. So when we say shunt, can you tell me what is the meaning of shunt, any one of you? In electrical engineering, when we say shunt, what does it mean? Shunt means parallel. So if you have a shunt excited DC machine, we say shunt excited DC machine, which is one kind of self-excited DC machine. We have the series in parallel with the armature in this fashion. So in shunt machine, in the terminal box, you may not get 4 separate terminals. You can get only these 2 terminals. This terminal, maybe they will name it something, maybe A, maybe A, whatever they might name it. Only these two terminals you will get. Not necessarily there will be 4 terminals. Maybe in your laboratory machines there might be 4 terminals where you are intended to connect it in shunt, but this is what we mean by shunt excitation. So what we can understand from here is in shunt excitation, the armature voltage is always equal to the field voltage. This shunt is excited. And okay, we will see another, then we will make some comments. Another part is, so we have got parallel, so we will have series also, right? So when we have series excited, just a minute. So when we have series excited, as you can now guess that the field winding is in series with the armature. So in case of shunt winding, we had same field voltage. So here we had field voltage same as armature voltage. In case of series, can you tell me which one will be the same? Which quantities in field and armature will be the same? They are in series. When two electrical components are in series, which quantity through them is the same?
Current.
The current through them will be the same. So here we have the field current as the same as the armature current in this. So we have shunt and series. These are the most two fundamental excitation of DC machine, and there are mixtures of them. There are mixtures of them. The mixture is compound. Compound excited. That is, there are both shunt and series connection. So how would they look? Problems we will look later. We'll test it. So shunt and series, if they are compound excited, we will have both. We will have series here. We will have a shunt here. So both kind of windings are there. So what I told you that we conventionally draw it. Okay, let me draw it. So two windings. The shunt one is here. The series one is here. This is the shunt winding connected like this, field winding, and this is the series winding. This is the DC bus. So this winding 1 is shunt, this winding 2 is series. Can you tell me another way with which we can do compound? Is there another option of doing compound excited?
Short compound and long compound.
Yeah, so short compound and long compound. So what kind of compound is this? Is it short, not short compound, short shunt, long shunt? So is it short shunt or long shunt? Any idea? We'll paste it here. Far away. Any idea of the short shunt? See, the name says it all. When it is shunted, there are two options. This shunt winding can be in parallel with the armature only, or can be in parallel with both the armature and the series winding. That is, it can have a connection like this. It can have a connection like this. So, no, the series is here, and where to draw? Okay, let me draw the shunt separately. So we have the series excitation here, and the shunt is in parallel with both. So here the shunting path is small, here the shunting path is long. So this is short shunt. very long shunt. And then maybe you can simply write equations and derive things. They are not that difficult to understand. Maybe some characteristics here and there. But we will discuss more on mostly these three machines: separately excited, shunt excited, and series excited machines. So for the time being, let us mostly focus on shunt and series. Although the separately excited machine is a very easy machine to understand, easy machine to control, easy machine to work on. We'll look into it. For the time being, let us now look and make some comment on the field winding.
What are the applications of the DC compound motors?
DC compound motors, I'm not very sure. I have to see. I think since they have some typical characteristic. No, I do not know. I will see and tell you. Maybe next week, if you come, I will come with the answer. What are their applications? But okay, about application, I will tell. You need not raise hand. You can talk. Anyway, so see, what is the role of the field winding? The role of the field winding is to create the field or the magnetic field in the whole structure of the DC machine. So if I draw a simple structure of DC machine, as we said in the last class, that we will mostly try to work with the developed view of the machine. Easy to understand, easy to draw, easy to write equations. So say this is the, okay, in developed view they are flat topped. And this is the, say, field, this is the armature, say, there is a rotor, and the field windings are here, they create flux and create magnetic field inside the whole body. So the role of it is creating magnetic field. Now, if you look at the equations for the magnetic circuit, what do they say? It says that MMF, magnetomotive force, which is nothing but number of turns times current, is equal to reluctance times flux. This is the reluctance of the magnetic circuit. Now, this reluctance of the magnetic circuit completely depends on the shape of the circuit. See how much gap you have here, how much wide these teeth are, what is the path that the flux is taking, what is the material of this. So that is kind of constant here. And this flux, how much flux you need, that comes from the design and operational point of view of the machine. So you can consider for a given DC machine and its design, this thing to be a constant. Now you have this N and I to play with. N and I to play with. You can have for a given value of MMF, you can have two cases. You can have small number of turns and a large amount of current flowing through it. You can have a small amount of current flowing through a large number of turns. If you have the Ni product same, both the cases you will get the same flux out of the magnetic side, out of the field winding. Now the question is in which case which one is chosen? Can you get some idea or can you have some guess, obviously some logical guess out of it? In which case shall we go for a smaller current? Which case shall we go for a larger current? Think it in terms of current. Is my question clear? These are two cases, case 1 and case 2. One of them is used in shunt machine, other one is used in series machine. So can you tell me in series and shunt machine, which one is used? Case 1 is used in series or shunt. Think in terms of current.
In a shunt, we can go for small number of current, less number of current and large number of turns.
Why so?
Because in shunt, voltage across the terminals are constant, so we can draw less amount of current, or we may have to work with less amount of current, and that's why we can have to go with the large number of turns.
Okay, we can think it in some other way also. You see, the field winding does not provide any power ideally. It only maintains the magnetic field. So, but to excite a field winding, you need some power. So, what is that power? So, basically, a field winding is nothing but that large winding with a resistance. This resistance is not connected to it. This is the resistance of the winding. If you have winding, there is a resistance. We draw it as a lumped parameter. There is a series resistance. Now the thing is, you have some say 220 volt supply in the field, right? And all the power at steady state, the current is constant. So at steady state, you can even neglect the inductor here. So the power drawn by the field winding is V times I. So if you have a large amount of current, flowing through it, you can design it that fashion. You can give small number of turns and large amount of current. But if you have a large amount of current flowing through this winding, what will happen is you will achieve your objective. You will get the required flux, but there will be a large power loss in the field winding, and you will also end up supplying more power than required. That is not required, right? On the other hand, you can go for a small amount of current and large number of turns. That will give you the same MMF but at a lesser power loss. So this is done in shunt machine. This is also done in separately excited machine. But in series machine, you have no other option. Because the whole armature current is flowing through the field winding. And armature current is usually large because that is the load current. The whole power, see, if you have 200 kilowatt of DC machine to some voltage supply, the whole load current is flowing through it. So in shunt machine, in series machine, you have no other option. So there has to be this large current and small number of turns. So in series machine, the field winding has lesser number of turns but thicker wire so that this large current can flow. Whereas in shunt or separately excited machine, you have large number of turns but with thin wires. Remember one thing, we could have done this thing. We could have done thicker wire and less number of turn in shunt in series machine also. Sorry, in shunt machine also. But that would cost us a lot of power from the source. Okay. And also, one more thing that is even more important. That is, say I have I have large current flowing here. If I get a large current flowing here also, ultimately the total current requirement from my DC bus becomes very large, which is maybe another problem to arrange for a DC power supply of maybe twice the current. Right? Handling current is difficult. This is another reason why this is not done, why we have smaller current in shunt machine. Okay, so that being said, I will end with, in this week's lecture, there are several things on windings and all, but my experience says as of now, I am in my third year of PhD. So my experience says that much of winding and all in DC machine, we really do not need to know in this year of 2022. That is not required. That is not used that much anywhere. What we do is, when we talk about DC machine, we simply draw its equivalent circuit like this. So this is the armature. This is the equivalent series resistance of the armature. This is the terminal. So this is the terminal voltage V. This is the induced EMF E. This is the armature resistance RA. right? Since DC machine draws or supplies DC current, we do not draw the inductance. If you were concerned about inductance at steady state, if you were concerned about, transient behavior of DC machine, that is when you start a DC machine, how the speed becomes steady, how the armature current becomes steady. If you are interested in this kind of characteristic of DC machine, then we also consider the inductance of the armature circuit, which also comes in series with this. But in electric machines, in this paper, we are concerned only with the steady state operation of DC machine. So we only draw this armature resistance. Once again, this armature resistance RA, this is an equivalent series resistance which is distributed throughout the armature winding, and we draw it as a lumped parameter. We draw it as a lumped parameter, as if it is not distributed, it is lumped at one place like this. Okay. Oh, sorry. Now there are two equations. The back EMF. As Faraday's law says that EMF induced E is d psi dt. So for the same flux, if you cut the same flux at higher speed, you will have higher EMF. So this back EMF E is given by K phi omega, all of them in SI units. Okay. And another thing is torque. Torque is K phi IA, right? So these two are the most important equations in DC machine, and while studying DC machine, or at least applying DC machine, using DC machine, this is enough to know. Other things you can derive from here, and windings and all we do not really need to focus on much. Now the question is, what I thought I will cover last week I could not do, is why DC machine? Why DC machine? See, DC machine is actually, the good boy of electrical engineering. The good boy means, everyone wants to be like the good boy. Why is it a good boy? Good boy because in DC machine, the torque is proportional to the current, and the armature flux and the field flux do not affect each other. I will show you this thing that I used in my last lecture. I will copy this. Sorry. I will copy it here and show you what I mean to say actually. See, we mentioned this, discussed this thing in last class. So forget the direction of rotation. So you see here, I have a current band where all the currents are going away from us. I have, say, another current band here where all the currents are coming towards us. So from here, can you tell me what will be the direction of the magnetic field produced by armature? If forget these blocks. Can you tell me what will be the direction of the magnetic field produced by the armature? It's understandable, right? This is armature, this is field. This is armature, this is field. Yeah, go on.
North to south.
Can you be more discreet? Left to right, top to bottom, or something like that? Anyone else wants to try? We have current direction and we have to find out the direction of magnetic field. This is simply right hand thumb rule plus 12 things. Okay. So this armature field is downward. Yeah, going inside, coming out. Armature field is downward. So phi armature is downward, whereas this field winding magnetic field is from north to south. So you see, in a DC machine, the armature flux and the field flux, they always operate perpendicular to each other. As you have studied in vector classes, that if you have a vector v, then the component of it in a direction theta is v cos theta in this direction. So when you have a vector at its quadrature, that is 90 degree, you have 0. That is, a vector does not affect anything which is quadrature with it, 90 degree. In DC machine also, the two fluxes are at quadrature. We say quadrature, perpendicular to each other. So armature flux and field flux, they do not affect each other. They do not affect each other. So what is so great about it? Why are we so happy that they do not affect each other? See, if you want to control the torque from outside, say you have a DC motor and you want to control the torque, all you can do is you can control the current. As soon as you are controlling the current, this flux phi, these are field flux, they are not affected. So if you promise that, okay, I will not change the field flux, you can directly write torque proportional to the armature current only. So you are having a linear relation of the torque and the current. So you can simply control it from outside the linear controller and you will get a simple control on torque. If you look at induction machine, we will not discuss it much now, but if you look at induction machine, this is not the case. In induction machine, the angle between them, the angle between the stator flux and the rotor flux, they are not, that is not 90 degree, they are not at quadrature. So if you control the current of the stator, both the fluxes change because they affect both of them. Say phi A, if the armature flux is here and the field flux is here, it has phi A has some component towards this, right? So if you vary one, the other one automatically changes. So in induction machine, first of all, the control is not decoupled. We say in DC machine, the torque control is decoupled. It is linear. In induction machine, they are not decoupled. So there are large theories about, you might have heard about these terms, vector control, or the most generalized term is field oriented control. In case of induction machine, synchronous machine, where your target is only to make sure that you can decouple the variables such that you can have torque proportional to some current. Induction machine is called IQ, quadrature axis current. So this is the point of teaching DC machine even today. That is, it is the ideal machine that we all want to achieve. Even if you have an induction machine, we control in such a fashion using field oriented control that it acts as a DC machine. That is the ideal in front of us. This is why DC machine is still being taught. This is the good way of electrical machines. But the question is, if DC machine is so good, why is it being replaced? So fast it is being replaced. What is the problem with DC machine? The problem with DC machine is its commutator and brush gear system. I have discussed in detail what is commutator and brush gear system. A commutator and brush, whatever. So that is nothing but a sliding contact. So what do you have in a commutator? In a commutator, you have copper pieces like this. This is one copper piece. This is another copper piece, and they are connected to several separate winding ends. Another copper piece like this, they are placed. Maybe this goes to one winding, this goes to another winding, this goes to another winding. So they must be electrically isolated from each other. So we have some kind of mica isolation in between them. Mica isolation in between them, electrically isolated, isolation or insulation, whatever. But the thing is, this insulation has got some voltage capability, blocking capability. What is the maximum voltage that this insulation can block? There is a limit. Now the thing is, when we go for high power, we always prefer high voltage. Keeping the voltage same, we could have increased the current also to get high power. But the thing is, handling current is very difficult. Handling voltage is relatively easy. So high power means high voltage and current may be some level. But the thing is, when you are going for high voltage, the voltage between these pieces become large, and this mica insulation might not be capable of handling that much of high voltage. There is the first problem with DC machine. There is a voltage limit, and as a result, a power limit. You will never see DC machine of megawatt range. Even if you see, they are extremely old. The second problem is again with this commutator and brush gear arrangement, the sliding contact. You have something moving here, which is moving in this direction, and something static on it. So, as you can understand, there is wear and tear. You have to regularly maintain, regularly replace these brushes. There is heat generated here. So we have wear and tear, we have heat. Not only that, now suppose you are using motors in different industries, right? Now many industries work at very harsh conditions, specifically the chemical industries and all. So in a chemical industry, there may be some chemicals present in the air which are combustible. So they will come here through the air and they will ignite. There can be sparks here also which will cause that ignition of those things. So DC machine is not at all suitable for operation at harsh conditions. DC machine is in that way is not robust, requires frequent maintenance, and is not suitable for harsh environments. On the other hand, induction machine is very robust, specifically the squirrel cage induction machines, but the problem with them is the control, what I told you. Okay, and what else I was thinking, I will tell. Voltage, robustness. Okay, any question till now? Any question till now? Nowadays, all the modern machines, I will name some modern machines that are very much used nowadays, very much researches are going on them. For example, PMSM is probably the most famous. If not PMSM, then BLDC is the most famous. SRM, switch reluctance. So PMSM is permanent magnet synchronous machine. BLDC is brushless DC machine. SRM, switch reluctance machine, synchronous reluctance machine. These machines and some other even more unconventional machines are very much popular nowadays. One thing.
So repeat the third one.
SRM is switched reluctance machine. Switched reluctance machine. So among these modern machines, one thing is common in all of them. In all of them, one thing is common. What is common? There is no sliding contact. This commutator brush gear is the weakest point of a DC machine. This is very much vulnerable to almost everything. So all these modern machines that we are working on nowadays, one thing is common between them. There is no sliding contact. If today a new researcher comes up with a new machine that requires sliding contact, you will be thoroughly questioned. You will be thoroughly questioned why at all is it required, and if you cannot show some significant improvement compared to what we already have, that machine will not survive in the market. Only one case, that is the DFIG. DFIG is doubly fed induction generator, which is nothing but an induction machine. Doubly fed induction generator. These things still use sliding contact, but there are reasons behind it. The first thing is this is used in wind power application. Wind power application, very popularly, very widely used in wind power application. And a wind power may be this is the pole on which the turbine is mounted. And this is maybe some 100 or 200 feet, maybe some I never saw in front of me, maybe some 200 feet above of the ground. And it is closely covered. And secondly, although there is a sliding contact, there is no commutator, there is slip ring. Slip ring is a solid piece of cover on copper on which there is a brush. So no mica insulation, a solid piece of copper. So this is the one very unique example, although not very rare. Otherwise, all the machines, especially electric vehicles, all the machines electric vehicles are going to use and using, all of them are free from any kind of sliding contact. So that's about it. That's why DC machine is very much desired, and why is it very much undesired. So what we try to get is a machine which will not have sliding contact, but will have characteristic like DC machine, torque proportional to current. So these machines, PMSM, BLDC, and also induction machine, they're subjected to some certain kind of control such that we can achieve this torque proportional to some current, linearly proportional to some current. Okay, we'll not go into very depth of these things. This is only to give you an idea of what the modern machines are doing. DC machine, maybe some industries are still using DC machine. They are not replacing them because replacing will cause a lot of cost. But once those DC machines go out of service, definitely they are not going to buy a new DC machine. That is for sure. Okay, with those things in mind, we will do two problems today and wind up. So it says, read the question, okay? 125 volt separately excited DC generator with armature resistance 0.2 ohm is first run at 1300 RPM. Open circuit voltage is set to 140 volt by adjusting the field current. We will look at this statement once, okay? Anyone wants to say something? Okay, this statement is a bit confusing, so I will clarify. So this separately excited DC generator has a nameplate rating of 125 volt. So as you know that when generators run, okay, I will draw it properly. This is a brush. This is the armature resistance. So this is a DC generator. So when a DC generator runs, I told last year generator means mechanical power to electrical power. So there is some prime mover. There is some prime mover which is running this DC motor from outside. We need not know what it is. That can be a DC, that can be a diesel generator, that can be a turbine, anything, whatever. So this is the armature, it's rotating. Now you see, its nameplate rating says it is 125 volt. There is a field winding also. There is a field winding also. Okay, some voltage, a variable voltage. So the nameplate rating is 125 volt and the machine is run at 1300 RPM. So the prime mover settings is set such that it rotates at 1300 RPM. And then the field voltage is regulated. It is varied such that the open circuit voltage that we get here is 140 volt. So is it clear up to this? Open circuit voltage is set by regulating the field voltage or field current, to be more precise. We do not control current, we control the voltage, but what the machine can understand is the current in the field side circuit. We have seen MMF is number of turns times current. Voltage has no role there. All right. Now the question is, when it is loaded to deliver 48 ampere, it is a generator, right? So it is delivering 48 ampere. The speed drops to 1200 RPM. Estimate the terminal voltage at this loaded condition if the field current is unchanged. So now, this machine has been loaded. It has been loaded. This is the terminal voltage. And we have the generated EMF here. This EMF is generated due to the interaction between the current and the field. Field is given by this, right? And because of loading, the speed drops to 1200 RPM. Question is, what will be the voltage here, right? Now you see, when you have a DC machine, this EMF E, you cannot measure. Can you measure this EMF? Can you tell me why you cannot measure this EMF? Can I not simply put a voltmeter here and measure the EMF? This E is also called back EMF. So can I not simply put a voltmeter here and get the EMF, the generated EMF in DC generator? In motor, it is called back EMF, not in generator. No idea? Okay, can some of you raise your hand who has done DC machine experiments in university? In your college, how many of you have done DC machine experiments? An electrical machine theory course should always be accompanied with a laboratory course actually. Anyway, see, the thing is, I told you this, that this resistance is not something that we connect. This resistance is not something that we can see. There is a long armature winding. This is the armature and the coils are wound around it. And this whole resistance that is distributed throughout is the armature resistance, which we estimate, experimentally find out, and draw in our circuit. But there is as such no such resistance here. So basically this point, this whole node, this is not available to us. Only this terminal is available to us. So we can never know the EMF developed by the machine. We can never measure, but we can calculate. Now the thing is, when the machine was not loaded, when it was like this only, the field circuit was turned on and it was being rotated by the prime mover. It was not loaded, so there was no current through it. So if you connect a voltmeter here, whatever the developed EMF, that much we will get in the voltmeter. So you can measure the EMF only if there is no load. As soon as there is a load, connected here, a current comes and there is a drop. So you cannot measure the EMF anymore. If you know the armature resistance value, you can add or subtract the voltage drop with the terminal voltage and then can find out the EMF. In this example, we will see how we do that. In the next example also. Okay, I don't know why I'm... Okay. If things are not clear, tell me, okay? This is very crucial part of it, because DC machine windings and all you will never require, but DC machine you will keep on using in small applications. Okay, so at 1300 RPM, the open circuit voltage was 140 volt. Open circuit means no load. So definitely this is the EMF E. Now we have seen that EMF E is K phi, sorry, not I, K phi omega. Oh, I forgot to tell you one thing. I will come back. These two equations, see, I wrote E equals K phi omega, T equals K phi IA. The K value that I wrote here, see, I did not write K1 and K2. I wrote K in both the cases. If you write these equations in SI system, EMF in volt, torque in Newton meter, flux in Weber, omega in radian per second, and current in ampere, all of them if you write in SI or maybe in one given unit system, the value of K will be the same. It is sometimes called as the machine constant. They are same magnitude wise. So, okay, but be careful about the unit, because sometimes we write speed as RPM. You have to convert it to radian per second. RPM is not the SI unit. Okay, we will quickly do. So E is K phi omega. It is given that field current is unchanged, so E is proportional to omega. Right? Now on loading, the omega changed, so the EMF has also changed. So we can write, we have to find out the EMF first, so as to find out the terminal voltage. So 1300, okay, let me write E on the left hand side. So 140 volt came for 1300 RPM. How much EMF E2 I am writing will come at 1200 RPM. Can someone do? Okay, I will doing it. In the meantime, you tell me, can I do these things in RPM? These equations, I directly wrote them in RPM. I did not convert them into radian per second. Can I do it in RPM? Today I will call people who never respond. Tejashi, can I do this calculation in RPM? RPM is not the SI unit. Tejashi, can you hear me? Tejashi, are you there? Vidya, can you answer this question? Do I need to convert these speeds to radian per second? Tejashi, are you there? Vidya, are you there? See, these classes are not mandatory, okay? Your attendance is not taken. So there's no point of coming and sitting or maybe just logging into Google Meet and leaving. Anyway, if you are interested in solutions only, take the solution. So we are doing a ratio, okay? So if I want to convert these to radian per second, I will multiply it with some factor. And the same factor I will multiply this one also. So they will get cancelled, no point. So the thing is, I loaded the machine, the speed dropped. Speed was same. So definitely the back EMF has dropped. How much is the back EMF now? 129.23 volts. So it was 140 volt open circuit voltage. I loaded the machine, speed dropped, as a result the back EMF dropped. So we got this voltage. So now it is 129 volt. The question is, what is the terminal voltage? Now it is very easy. This back EMF you can simply represent as a battery of 129 volt. 129 volt battery. It is supplying a 48 ampere of current. So as a result, there is a voltage drop here. This is 0.2 ohm. So can you tell me what will be the terminal voltage? Someone? What will be the terminal voltage? Or at least what I should do? Nachiket, you were responding.
Simply V is equal to IR.
V equals IR will give me the voltage drop here then. What rule of electrical engineering, what rule of electrical science should we apply? These three letters ring some bell.
Voltage law.
Kirchhoff's voltage law. Simply circuit solving. You will get maybe some 116 volt or something I just did. Oh, 119 volt. 119.63 volt. So basically, if you load this machine, keeping the field current unchanged, load this machine such that the load current is 48 ampere, the terminal voltage will be 119 volt. Okay, so given the response that I got in the last question, I don't know whether I should start this question. This is even more difficult than that one. The armature and field resistance of a 200 volt DC shunt machine are 0.25 ohm and 100 ohm respectively. Okay, I will not start this question. I think you people need to read these things once more. Siva will cover this question, okay? So next Tuesday, not next Tuesday, every Tuesday, you have Siva's class. Siva probably takes his, he will get a reminder also. Probably he takes his class 7 p.m. He will discuss this problem. We'll just look at it once. The armature and field resistance of a 200 volt DC shunt machine are this and this. Let us first look at these figures, forget the problem. See, this is a shunt machine, right? The armature resistance is so small and the field resistance is so large. It is how much? 400 times the armature resistance. This is the typical value of the, or typical relation, not relation, shouldn't say relation. Typically, the field resistance is much large compared to the armature resistance in case of a separately excited or shunt excited machine. For series excited machine, they are very close to each other because the whole armature current flows through it. Okay, if the machine is connected to 200 volt supply, then estimate the ratio of speed as a motor to the speed as a generator. The line current in both the cases is 50 ampere. Okay, you people tell me, should I do this or should I leave it for today? We are almost 1 hour.
If possible, we can do it.
Okay. So we have a DC shunt machine. Maybe then Siva will solve other questions. There are some more questions. He will discuss about them. Okay, so we have a DC shunt machine. Sorry. And it is invariably connected to a 200 volt supply. And there is the field winding here. This thing is 0.25 ohm, this thing is 100 ohm. In one case, it is motoring. That is, there is some load connected to this, and the load is adjusted such that it draws 50 ampere current from here. In the other case, it is generating. That is, the torque here is adjusted such that it feeds a 50 ampere current to the system. Okay. Now we will take the first one. We will first see the motoring action. Motoring action we will see. So 200 volt DC shunt machine. Is this thing? The machine is connected to a supply. We estimate the ratio of speed as a motor to the speed as a generator. Line current is 50 ampere. So we have to find out the speed. How to find out the speed? I have to think a bit about it. If this is back EMF, then we have to find out the back EMF here. Okay. So can you give me some idea how to do this? I have to. So some current IF is flowing, some current IA is flowing. All right. So you see the current IF that is flowing here, this is a DC current. This is a DC current. So this inductor has a zero voltage drop across it. This inductor will have a zero voltage drop across it. Is it clear? Because voltage across an inductor is L di dt. So if the current is a DC current, then it has a zero voltage drop across it. So if you have a 200 volt drop here, you must have a 200 volt drop in the shunt branch also. And so this whole 200 volt must be coming in this 100 ohm resistor because this is 0 volt. So what is the field current? Field current is 200 volt by 100 ohm, 2 ampere. So out of this 50 ampere, 2 ampere takes this path and creates a 200 volt drop. And the rest of the 48 ampere goes here. Now this 48 ampere creates some drop of 12 volt here, right? 48 into quarter is 12. So rest, so 12 volts, see this whole thing is 200 volt, 12 volt is gone here. So the back EMF EB in this case is 200 minus 12, so 188 volt. Okay, we have been asked to find out the ratio of speed. We know that E is proportional to omega. So if you can find out the ratio of, say, as a motor and a generator, we can find out the ratio of speed as a, as a motor and as a generator. Fine. So we have got the back EMF in case of the motor. Now we will have to find out the back EMF when it operates as a generator. Before we do, can you give me some idea whether this back EMF will be in case of, oh sorry, I am telling this wrong again and again. In case of motor, it is back EMF because that is the reaction of the machine. In case of this generator, it is not back EMF, it is the generated EMF because that is what we get from the machine. It is not something back. In case of generator, it is back torque. That is the reaction of the machine. Okay. So what will be the generated EMF of DC generator as a generator? We will find out. But can you tell me what value are you expecting? More than 200 or less than 200?
It will be same.
Same as motoring?
Yeah, same as a motoring.
It will not be same as motoring. I will tell you why. You see, in the last question we saw that Where is it? In the last question we saw that the generator generates some EMF, and when the load comes, the voltage drops. So this generated EMF must be more than the terminal voltage. So it must be more than 200 volt. How much more, we will see. So it is now again 200 volt connected to a 200 volt supply. And line current, see, it was given line current, right? Line current means whatever current you are getting or giving to the source. So this is still 50 ampere, and whatever discussions we had here, field current, why the field current will be 2 ampere, they still hold, because this shunt branch is still having a voltage of 200 volt, and this inductor still has a voltage of 0 volt, and this is 100 ohm. So a 2 ampere is flowing here. 2 ampere current is flowing in this branch like before. So 50 is going out, 2 is here. So there must be a 52 ampere of current. This is the armature current. So you see the same machine connected to the same grid, the same line current. As a motor, the armature current was 48 ampere. As a generator, the armature current is 52 ampere, because now this armature current is also, this field current is coming here. That is why this is more. Okay. So 52 ampere is here. Now the voltage drop here, oh sorry, I drew the voltage drop things opposite. It will be plus minus the opposite thing. That is why 188 plus 12 was 200. It's now in this direction. It is 0.25 ohm, so it is 13 volt. 13 volt is dropping. So this EMF is something, out of which 13 volt is going away, then only we are getting 200 volt. So it must be 13 volt more than 200 volt. It must be 213 volt. So now that we know the back EMF in both the cases, we can find out the ratio of the speed. It is the ratio of the back EMF in case of motoring and in case of generating mode. Whatever you get, that is the answer. So is it clear? We have already crossed our time, much more. Okay, then we will meet next week, Saturday,
Yes,
this
sir.
time. Means 7 p.m., not this time, 7 to 8 p.m. Once again, we will come with DC machine operation. Chalo, bye-bye.